Welcome to the next lecture in quantitative methods in chemistry. In the last class, we tried to understand how to use simple software like the spreadsheet to make, first of all, to record our data and analyze it. We also saw simple fits, as you might have seen in the previous week, how to do fits and what does a fit mean. Basically, in the last class, we used that idea in order to understand how to calibrate burette and where all errors could come up. In today's class, we will be extending the similar idea in order to use the spreadsheet software to see how data analysis can be done, something for a more of a problem, let's say. So the problem that we will be defining here would be to determine the heat of solution of benzoic acid. So basically, this experiment will help you find what is the standard enthalpy change that is associated with dissolving solid benzoic acid in water. And one would understand that benzoic acid, although it has a carboxylic group, although it has a COOH group, doesn't dissolve that easily in water because of the presence of this aromatic moiety. We will try to understand how this experiment will be set up and what can be done. Just to give a little bit of basics before we plunge into the background of what this experiment is, one has to understand how can we determine delta H naught. It comes from the Van 't Hoff's equation, which relates equilibrium constant to the reaction enthalpy change as a function of temperature. So this is the relationship from which you are going to be determining what is the enthalpy change associated with such a process. Why don't we take a look at what all steps are involved, as we have done in the previous series of lectures. What are the steps you are going to be performing? What are the apparatus that you would be needing? After having known that, what are all the possible sources of errors that could come up, basically systematic errors, and how they could be minimized, and what is the data that has been recorded, and can we in fact determine the heat of dissolution of benzoic acid. As we would start with the materials required for all the experiments, the first thing that you would end up needing is a bunch of flasks. Basically, you would need one of about half a liter and another of about 50 ml. One would be used for equilibration so as to get the temperature at which you are doing a measurement, while the other one would be useful towards dissolving your benzoic acid. You would also require beakers. We will see why you would require them. So always it's a good idea to list exactly what you need and how much of what you need so that you can prepare appropriately. You would also need measuring cylinders, graduated pipettes, so as to measure out a given amount of volume that you want, and the burette. Remember, you just calibrated a burette last week, so you would realize that similar to the way of calibration of the burette, one could also calibrate the graduated pipette so as to make sure that errors that come out of it is also minimized. You need conical flasks, a funnel, a glass rod for stirring, and mortar and pestle. You are going to see that you have to crush the solid that you are going to end up using. We will try to understand why that is the case. And a water bath. If you remember the last experiment, I told you to make a note of the temperature so as to determine the density of water at that given temperature. This is one experiment where we will be doing the same equilibrium measurement but as a function of temperature, meaning that you will keep changing the temperature to measure something. And for such a reason, you have to maintain the temperature at which you want to measure it, and for that matter, the water bath is going to be extremely useful. Now, of course, a thermometer to measure the temperature. You will understand why we have to use cotton in order to make sure no solids come up when you are making a measurement. You would be using oxalic acid. If you would realize, we are going to be measuring benzoic acid concentration, and one way of doing it is by taking sodium hydroxide solution and titrating it against benzoic acid. But one might remember that if you are taking pellets of sodium hydroxide and keeping it outside, it's extremely hygroscopic. It's going to absorb water from the atmosphere, making it a secondary standard. Since sodium hydroxide is a secondary standard, you cannot do titrations unless the sodium hydroxide is standardized. And for that reason, you will be using oxalic acid. You are able to realize how one measurement feeds on to another measurement. So therefore, one has to be careful in preparing the 0.1 normal oxalic acid solution, else that is going to be introducing some systematic errors that might come up. And of course, the sodium hydroxide solution at a certain normality that you know, but of course this has to be standardized with oxalic acid, then the benzoic acid so as to perform the experiment, and phenolphthalein dye, which will help you do the acid base titration to visualize the endpoint. As always, you must have a very detailed experimental procedure that one has to follow. The first step would be to standardize the sodium hydroxide solution against oxalic acid. This I have already mentioned, since oxalic acid is a primary standard and sodium hydroxide is a secondary standard, you would have to end up normalizing the sodium hydroxide solution. Make sure concordant values are obtained. This is something that we would have heard from our high school days, where when you are doing titration, concordant values must be obtained. The mere reason for getting same values in multiple measurements is to ensure that you have repeatability. If there is a problem of repeatability, it could be due to several reasons. Maybe there is a droplet of the solution or the burette solution that's on the end of the conical which has not been properly added, which will result in different endpoints. And this difference in endpoint would once again result in a systematic error that will get propagated throughout. If you are able to realize you are standardizing NaOH against oxalic acid, if you introduce about a 5% error there, that keeps on propagating throughout your measurement, making it less precise. So therefore, one has to be careful doing this. So concordant measurements are important in any titration that you might end up performing. And generally, we would like to make tables like the table that we made for the last class to standardize or to calibrate the burette. Here also we will make a table, so that the first step of this table would be the standardization of sodium hydroxide solution. Okay, now having done that, take a small amount of benzoic acid and grind it into into fine powder using the mortar and pestle. This is important. One has to ponder why something like this has to be crushed. You will soon realize that whenever something is a solid and you want to dissolve it, if you are able to increase the surface area, that will help you dissolve things better, which is why we tend to like refined salt, so that it's simple granules which can be mixed. Same with the case of sugar, where you end up adding it to any solution, it dissolves right away. And there are also other reasons to it which we will understand when we go through the theory of the experiment. While step 2 is being performed, set up a water bath to the desired temperature. So this is how you will be making sure the temperature is equilibrated, and therefore you will be able to measure certain given value at any given temperature. So here we are saying set it at 30 degrees. We will see that although the water bath has a certain setting in terms of the knobs, one has to be careful using a thermometer to ensure that you are indeed measuring that temperature. Yeah, that's exactly what is written here. Although the water bath claims a certain actual temperature, ensure the same with the thermometer. Otherwise, once again, this is going to end up resulting in a systematic error. And remember, this need not be a constant. It could be a proportional systematic error which cannot be redone unless you calibrate the water bath thermometer temperature. So it's rather than going through that complexity, it's easier for you to measure the temperature at which the water bath is, so that you can make the analysis in a much more easier fashion. Now, to a clean conical flask, add about 200 ml of water, and to this conical flask, add a small amount of benzoic acid. So basically, whatever benzoic acid you end up crushing to fine powder, you end up adding to this 200 ml solution of water, and set this conical flask to equilibrate at least for a minimum time of 15 minutes. So here is where you are talking about the equilibration time. You have to make sure that the solution ends up reaching the equilibrium temperature after dissolution of benzoic acid. Remember, when you are dissolving benzoic acid, it can be an exothermic or an endothermic process. In case that it's an exothermic process, what ends up happening is that you will be releasing some temperature to the solution, which will increase the temperature at which you are making the measurement, although you are assuming you are doing it at 30 degrees Celsius. So one has to be careful doing equilibration, otherwise you might get erroneous results. The same holds good for the fact that if benzoic acid dissolution is endothermic in nature. If it's endothermic in nature, it's going to reduce the temperature. So either way, be it exothermic or endothermic, one has to ensure that a minimum time of 15-minute equilibration is done. And this is also done to take care, where you ensure constant stirring is done for this process, so as to ensure at that given temperature you are completely saturated with the benzoic acid that you might want, which is the reason why we are not committing on the total amount of benzoic acid that is required. You are trying to say add as much as you want. You can actually add in excess, so as to exploit the Le Chatelier's principle of all the solids going into solution, because you have too much of the solids. Of course, there will be a tapering off point after which no more dissolution ends up happening. In the case of amount of benzoic acid, let's say that you added benzoic acid and all of it has gotten dissolved, then it's a good idea to add a little more so as to achieve saturation. So this is also another step. So there are multiple steps where one could go wrong. Here the measurement of temperature in the water bath could be one of the reasons why this that could be an offset that comes in a measurement. One has to be careful in order to ensure that the solution reaches equilibrium irrespective of an endothermic or an exothermic reaction, and one has to also take care that excess of benzoic acid is put into place so that the solution reaches saturation at that given temperature. If any of these steps are not followed, you might end up having a certain error that comes up. Okay. Now, from this saturated solution, the next step would be to pipette out 10 ml into a clean conical flask. So this is the conical flask with which you will be performing your titration. And when you are doing this, unlike the last time where you might use a pipette in the simple direct way without having anything, in this case you would like to have cotton filters at the end of the pipette. This is required because remember there will be some excess solid that will be floating around in your solution. And by chance, let's say you pipette that solid out, it's going to be erroneous because you want to measure how much of benzoic acid is dissolved into the solution and not how much of benzoic acid is present in total. So one has to be careful about it, due to which you have to put a cotton filter at the tip of it so that this is ensured. And let's say that by mistake you get some solids into it, you're going to introduce some error that goes into it. And in this case, it will be some kind of a random error, meaning that if your cotton filter is not working properly, or let's say you didn't use the cotton filter, you might have varying amounts of benzoic acid you will be adding in different titrations that you might end up performing, which will once again result in a huge error or even a gross error finally. So one has to be very careful about it. Having transferred the solution, then you have to standardize it against the sodium hydroxide solution. Remember one thing, when you are doing the experiments at a higher temperature, after having carefully transferred only the solution from the equilibrated temperature to your conical flask, you might see some solidification of benzoic acid. This is not surprising because let's say you are dissolving it at 50 degrees Celsius and you are performing the titration at 25 degrees Celsius, it could be that some of the benzoic acid starts to solidify because you are at a super saturated solution at such a condition. This is okay, and it's different from the solid that comes from the solution previously mentioned, because all that you are trying to take is the solution that has already been saturated at the higher temperature, and when you are transferring it, it's solidifying from that solution and not from any other source. So therefore that is okay. Then perform your titration, repeat steps through to 6 at various temperature, and these are the tables that we are trying to look at. The first table shows you you take a certain volume of oxalic acid, although it says 10 ml, we end up using 5 ml in the actual experiment, so that you are able to get a concordant value for measurement of volume of NaOH required. Therefore you standardize sodium hydroxide solution. Having done that, the next step would be to set up an elaborate table to get things going. So if you are able to remember some concept of equilibrium constant, which we will introduce in a moment, since benzoic acid solid is in its pure state and water is in its pure state, one can associate the equilibrium constant directly to the amount of benzoic acid that has been dissolved in solution that you are having. So what will end up happening, if you are able to relate the Van 't Hoff equation as I showed earlier, ln of K2 by K1 is minus delta H naught divided by R times 1 by T2 minus 1 by T1. You are able to see you are having a 1 by T that you are varying, and you are able to get a ln or log of K. So if you are able to plot the log of K as 1 over T, your delta H naught will come up as the slope itself. So let's quickly take a look at what is that you are trying to do. So the point that you would like to measure here is what is the delta H naught of this process. And remember, the spontaneity of a process is given by change in free energy, which is the sum of the enthalpy change to that of the entropy change multiplied with the absolute temperature. Here you are only trying to see what is the enthalpy change that occurs. So although you might have a process that's endothermic, it could still be spontaneous because of the change in total entropy of the system. So now what ends up happening is that in order to understand this entire process a little more easier, and also to motivate why is that you want to determine delta H naught, let's divide this entire equation by minus absolute temperature, minus T. On the left hand side you end up having something like minus delta G naught by T, which is equal to minus delta H naught by T plus delta S naught. Since delta S naught is the change in entropy of the system, minus delta H naught by T becomes the change in entropy of the surroundings. So if you are able to determine what is the delta H naught, and at that given temperature you would be able to say what is the change in entropy of the surroundings. So you know for a fact that delta H naught for an endothermic reaction is positive. So if delta H naught is positive, negative of a positive makes it negative. So this term ends up being overall negative, which indicates the entropy of the surroundings have minimized. Basically you are able to imagine this is that if you are able to add some salt and dissolve it in water, the outside becomes cooler. That just indicates the fact that outside entropy has dropped. So now after having understood what is the influence of the entropy of the surroundings, we would like to relate it to the equilibrium constant, which is what we are measuring. So one is able to understand a 1 over T dependence on the equilibrium constant. So therefore for a constant delta H naught as a function of temperature, you would be able to measure equilibrium constant as a function of temperature and determine what is the enthalpy change for such a process. So now what all dictates the entire process is that when you are having benzoic acid, you have solute-solute interactions that has a certain free energy, or rather that has a certain amount of enthalpy that has to be provided in order to break the interactions between them. As you would know, bond breakage requires energy. This process of breaking the solute-solute interactions is actually endothermic in nature, and this is also discernible from the fact that within benzoic acid you have the phenyl groups which ends up stacking on top of each other, and the carboxylic groups which might form intermolecular hydrogen bonds. So therefore in order to break the interactions between them and also the amorphous solid that it might have ended up forming, you have to break the interactions between the solid particles. So providing energy is also obtained by the mortar and pestle with which you are trying to make a fine powder of the benzoic acid. So we are able to realize that breaking AA interactions is generally endothermic. And the next thing that would that one has to remember, akin to the solute-solute interactions that one has to break, one also has to break the solvent-solvent interactions. In this case you are having water as a solvent, and you know for a fact that water ends up forming stable hydrogen bonds, and therefore you also have to break those interactions. And what would result in A being properly dissolved in B is to form favorable interactions between A and B. And in this case you are able to realize that the carboxylic acid might end up forming hydrogen bond with water. While that is a favorable interaction, you also have the phenyl group which is hydrophobic, which might not be happy in water. So basically this is also another term that overall comes up. So these three terms have to be kept in mind for this experiment, where there is a change in enthalpy that comes up for breaking solute-solute and solvent-solvent interactions, and the enthalpy change that is associated in forming the solute-solvent interaction. So one is able to realize that going from this, if you are able to get the delta H naught, one should be able to understand some information across these three different processes coming up. And of course if you are able to measure this in one way or the other, if you are able to measure this in some other way, and if you are able to get the total enthalpy change from this experiment, you will be able to estimate what is the enthalpy change that comes up for AB interactions being favorably formed. So this experiment is nothing but determine the equilibrium constant as a function of temperature, which I have repeated a couple of times, and this is just reiterating the fact that if you are able to plot the solubility as a function of 1 over T, in principle the ln of solubility as a function of 1 over T, you are going to be getting a curve that will help you fit the data and determine the delta H naught from the slope itself. Of course, that is a basic assumption that goes in this experiment, that the enthalpy change in this process is independent of temperature. I am not going to be alluding you to this, but if you are able to take a look at the Kirchhoff's law, which says how enthalpy change for a process changes as a function of temperature, you would understand not for all the processes you can assume the same, but in this case this can be assumed. The reason why I am also enumerating the assumption here is that any data analysis is contingent upon the assumptions that you have forced. In the case that this assumption does not fall in place, the whole data analysis could be biased. But that does not mean you cannot have any assumptions in your experiment, because some of the experiments have an inherent limitation in that you cannot afford to measure the changes that might end up happening. For instance, in this case probably we are insensitive to the changes of delta H naught as a function of temperature, or maybe delta H naught does not change at all. So not going into further detail, I would like to make you guys aware of the fact, please be aware of the fact that the assumptions might end up deciding your final result and the outcome of the experiment, which could end up introducing a bias by itself. So be aware of what all assumptions you are having and what assumptions are held good, and sometimes your data might say that is not a fair assumption, and you can reintroduce the approximation by going and redoing the model that you used to fit. But for this experiment, let's assume that the enthalpy change is indeed constant as a function of temperature. So now if you plot the log of S as a function of 1 over T, you get a straight line. Of course, the straight line gives the slope. The slope will help you understand what is the enthalpy change associated with the process. Since R is a universal gas constant and we assume it to be having no error, you would be able to realize that the error in the fitting of the curve would result in the final error in delta H naught. And this error in the fitting would come up due to the fact that you are going to be having different measurements. Basically, the solubility's error comes from the fact how off is the standardization of NaOH. The inconsistency in temperature could come due to the thermometer or the water bath that has not been properly set, or that you have not let the solution reach equilibrium, or that you have not formed a saturated solution. So these are all the reasons where you could get error in the different data points, and when you fit those errors will come up in the fit in the error, and that will result in an overall error for the delta H naught. So as always, let's take a look at the tables that one might end up preparing. So this is the first table where you will be standardizing, and this is the table that one has to be using. From the temperature you can determine the absolute temperature in Kelvin, and 1 hour temperature is therefore calculated, and the volume of NaOH that you would be standardizing the benzoic acid against will be done as 2 trials in order to get concordant values, and the concentration of benzoic acid can thus be determined. And from that you can determine how much amount of benzoic acid is dissolved in a certain amount of solution, and from there get a log of S and plot log of S as a function of temperature. Since we have already seen these tables, let's try to take a look at how this experiment is indeed performed. As you see here, this is the mortar and pestle, and we are adding a large excess of benzoic acid into it, and you will realize that using the mortar and pestle you are trying to make fine powder of the benzoic acid. Do as much as possible so as to increase the surface area of dissolution. Here we are able to see the conical flask that has 200 ml of water, to which you will be adding the solid benzoic acid, and ensure that the entire solution is immersed within the water, and use another conical flask which is also filled with about 200 ml of water, into which you will be adding your thermometer. And both these solutions have to be equilibrated in the water bath that you are trying to see at a given temperature, and the temperature, although is listed here, it's a better idea to have a separate measurement so as to ensure that you are actually measuring the temperature that you want to measure in. And to the clean water conical flask, add excess of benzoic acid as shown here, and once you have added, the next step you are able to realize the solid is all at the bottom of this conical flask. So this also results in the trouble that the benzoic acid is not going to be properly dissolved. So therefore use a glass rod and stir as much as possible in order to make sure the interaction between the solute A and solvent B is done. And now we are trying to show you an example where you are taking the pipette and how you will be adding the cotton plug to it, to ensure when you are trying to take some solution out of the conical flask, minimum amount of solid comes up. So you take the cotton and use a rubber band and fix it around it so as to make sure that all of the solid, even if it comes, gets stuck in this cotton. Use a rubber bulb, never use suction from your mouth as a source because it could be harmful. So once this is done, we end up once again stirring the solution. Make sure you have left the solution there for at least 15 minutes or more, and then you carefully pipette out a given volume of benzoic acid into this pipette. This matters a lot. Any error that might end up coming from pipetting will also result in final error. No bubbles should come up, so be very careful about it, or ensure that even if bubbles come up, you have the certain amount of volume that you require. Add that into the conical flask as shown here carefully, and now you might find some solids here. That is not a problem, as you might realize from 56 degrees, if you are going to a lower temperature, you are going to have some solids that come up. You might also realize some of the benzoic acid might have solidified in the pipette itself. It is a good idea indeed to wash the pipette with hot water so as to make sure that you are getting all the benzoic acid out. And to this conical flask, add as minimum as possible of phenolphthalein, as is a very sensitive dye, and then titrate it against the standardized NaOH solution towards the end point. And the end point is nothing but the appearance of the pale pink color. Okay, so now let's take a look at how a spreadsheet software could be used towards recording and analyzing your data. So in this measurement, the scientist finds that he gets concordant values of 22.1 ml required for the standardization of a carefully prepared 0.1 normal oxalic acid. So then the normality that will end up coming here would be V1N1 equal to V2N2. So this is going to be, since you added 5 ml of 0.1 normal oxalic acid divided by the total volume that you end up getting here. So you get the normality of sodium hydroxide around 0.2262 normal. So once that comes up, the next part is to do the solubility as a function of temperature, and as you're able to realize, this student has performed it across 31 degrees to 56 degrees, and you have to first convert degree Celsius to degree Kelvin. Since you are having these numbers, it's quite easy to do this, where you add 273.15 to this given value. You are able to realize a simple sum is given by the addition of 273 to that given cell, and you should be able to copy and paste all of this, so that this value that you are trying to determine is nothing but an arithmetic sum of 273.15 to this given cell. So now, having obtained that, the next step would be to determine what is 1 over temperature. So one can do that by just doing 1 over that given cell, and let's copy and paste this over here. So what ends up happening, you have 1 over T measurement, and this data is nicely analyzed. If you are, as a scientist, doing all this by calculator, you might end up introducing some errors here, which doesn't happen. Now, these are the values, concordant values of the solution of NaOH that was used to standardize or to determine the concentration of benzoic acid. As you are able to realize, what will end up happening here is that you are going to have a concentration that goes in the fact that it's V1N1 equal to V2N2 again. So what you are trying to do here is to determine the amount of benzoic acid that has been dissolved. In order to get this, you will take the product of volume and concentration of sodium hydroxide divided by the total volume that you have taken. You are able to realize this is the volume of sodium hydroxide, and this is the concentration of sodium hydroxide divided by the total volume, which you ended up taking as 10 ml. So therefore, you get the normality of benzoic acid. Of course, don't be in a hurry to copy paste this, because you're going to have a problem that, okay, this cell starts to take the concentration from the wrong cell, which doesn't make sense. As we have seen in the last class, if you want to not change a given variable, then what you end up doing is to write the same formula with a dollar in front of it. So what you would like to do is to write it at $2. So this will ensure that when you copy and paste it, while this cell gets arrayed, meaning that you want to pick the value from the volume of sodium hydroxide, this cell does not change. And of course, you want 10 ml, so that can also be input or put into another cell and called upon as a formula. So now we have gotten the concentration of benzoic acid in normality. I'd like to make you understand here, we are carefully using normality in this experiment and not molarity, because you are able to realize now you can compare oxalic acid to sodium hydroxide 1 to 1, because the equivalence has already been put into the normality. Okay, so now what ends up happening here for benzoic acid is that you want to determine the amount of benzoic acid dissolved. So therefore, how does normality go? Normality is nothing but the number of moles divided by the volume of solution in liters, the whole multiplied by the number of equivalents. Since the equivalence is 1, in this case normality is equal to molarity, and therefore what you are going to end up doing is to take the product of the normality to that of the volume of a solution. In this case, we are saying 100 grams of water, assuming that addition of benzoic acid does not change the volume of water. It's a fair assumption in this case, because this is all we can do. So this is the second assumption that we have put into place. So 0.1 liters is what we are going to end up adding here. Remember, you have to multiply this by the molecular weight of benzoic acid, because finally you want to get how many grams of benzoic acid you have dissolved. The molecular weight of benzoic acid is 122.12 grams per mole. So now this we can copy paste again. So this ends up saying how many grams of benzoic acid we have dissolved in water as a function of temperature. Let's start to make observations right away. You remember that in Le Chatelier's principle we learned, if it's an endothermic process, increasing temperature results in more of the forward reaction. We are able to see something of that sort, meaning that as you keep increasing temperature, you are able to see the fact that the solubility in amount of grams dissolved increases. So this already hints at the fact that you are probably looking at an enthalpy of the reaction being endothermic. Okay, let's not jump to conclusions, let's take our time. So now there are two ways of doing it. Whenever you are doing a log measurement, to carefully look at the library files that exist. Generally log indicates it's the log to the base of e, the natural logarithm, which many times we say as ln. Okay, but in this case you would like to get log of 10 because you are already factored that in, or we can do the calculation with ln itself. So let's try to do it both ways and see what we get up. Okay, so what you finally end up getting is that from the solubility you get log of the solubility. The last step that is involved right now is to plot solubility as a function of temperature. So you just select these two and then say insert scatter plot. So now you are able to realize the 1 over s, you can always add legends so that people are able to understand what is that we are writing. So in the y axis you have ln of 1 over s, and in the x axis you have 1 over t, that is the independent variable, and the ln of s is the dependent variable. You are nicely able to see almost a linear curve. Since we know for a fact the model that we are trying to look at is ln of s as a function of 1 over t gives us minus delta h naught by r, we can actually go ahead and fit it right away to a trend line, and then you set it as a linear trend line and you can look at the equation and the r square. Let me make this a little bigger. So you are able to realize that you have a slope of minus 1278.5 since you are doing the ln plot and it's 1 over t. Be careful about the units that you are trying to talk here. So therefore what ends up happening is that if you are using r in whatever units, you are going to get the delta H naught in similar units. And temperature is already in absolute Kelvin, so this is all fine. And if you are able to see the r square, which gives you the goodness of fit, you are able to see that's very, very close to 1. And we are able to adjust the same when you pay close attention to the dots and to the line that is fitted through it. You are seeing some points that are above the line and some points that are below the line. So this indicates that the fit is trying to satisfy all the data points, and this is what I meant by error. Small errors might have come up in your measurement due to subtle differences that might have cropped up due to maybe say extra benzoic acid solid that ended up coming, which will introduce error into your measurement. Nevertheless, you are able to realize that your slope is minus 1278.5. Now let's go back and try to see what is that we wanted to measure. What has happened is that Excel seems to be using log as log 10 itself. So basically you are having something a log of k2 over k1, you are going to have a 2.303 which comes up as change in the base from log e to log 10. So now your slope that comes up from this, which is minus 1278.5, can be used to determine what is the delta H naught. And if you are able to realize, since the entire term is negative here and this is also negative value, you are able to discern that delta H naught is indeed positive, indicating that it's an endothermic process. So now the delta H naught for this process is going to be 1278.5 times 2.303 times 8.314 joule per Kelvin per mole. So this is going to be equal to 24,479 joules. This is approximately equal to 24.5 kilojoules per mole. So one is able to realize that if you are trying to dissolve benzoic acid in water, the surrounding becomes cooler. And this is not a new observation. One has to remember that in thermodynamics we only want to ensure that the delta G naught is observed, not a delta H naught, meaning that there are processes which are endothermic yet spontaneous. For instance, if you are trying to dissolve sodium chloride, which is your common salt, into water, even that is endothermic process. That doesn't mean it does not happen. Basically that also happens because entropically there is something else going on with the system which ensures that the overall free energy change is still negative, although your delta H naught is positive. The same observation is done here. What you are able to realize is that we had enumerated 3 processes where you want to break the solute-solute interaction, solvent-solvent interaction and form solute-solvent interaction, and you are able to realize the first 2 processes, that is breaking of solute-solute and solvent-solvent interactions, are endothermic. Then if the solute-solvent interactions were exothermic, and more exothermic than breaking the interactions as mentioned previously, then the overall process becomes exothermic. This also happens in nature. If you are trying to dissolve sodium hydroxide in water, what ends up happening is that it releases a lot of heat. And for this purpose, one has to be very careful when dissolving something like sodium hydroxide, because it might introduce so much heat that the vessel in which you are dissolving it could actually break. So what we end up understanding from this experiment is that, okay, in order to measure something which is of interest to us, in this case the heat of solution, one can set up a smart experiment such that this can be reliably measured, and one has to have a very clear systematic stepwise protocol on what has to be done. While this stepwise protocol is written up, one also has to be aware of the systematic errors that could come up, where all it could come, and what could end up in a final large error that comes up. Here I am still not discussing the error that comes up in the delta H naught, which I will discuss in the forthcoming lectures, but one is able to understand the final value or the error that comes up in whichever decimal is contingent upon all the different errors that are propped up. One way of doing this is by repeating the measurement such that you will be able to get some value similar, and if you are able to repeat it several times, you get an average and a standard deviation from such a measurement. On the other hand, one could use the different points that they are measured and introduce a random error, assuming a certain amount of error that comes from other processes, and therefore get an error for the fit that comes up. These are different ways of doing it which we will discuss as we go forward, but I hope you have understood how to enumerate the different steps in the process that might end up giving error in your measurement. So in the first two classes in this week, we have seen how to use software to just input your data, and we saw how to use different functions within that spreadsheet functionality, meaning getting average, getting standard deviation, getting minimum, getting count, and features of that sort. In today's class, we extended it by trying to go for a very simple system which has a linear relationship, meaning that you change something, the parameter that you would like to measure varies linearly, in this case log of s varies linearly as a function of 1 over t, and therefore you are able to measure a parameter delta H naught. In the next class, we will be trying to take a look at how kinetics can be still measured and documented using spreadsheet software, and how rate constants can be derived from such a measurement. So basically, we have just increased our complexity from simply putting in numbers and analyzing the data in spreadsheet to a very simple linear dependence problem. Next will be a non-linear dependent problem, from which we will be able to understand how software is extremely useful to document large piece of data set. And I hope this will help you understand how important is even documenting data in software, so that this can be disseminated and also shared with the community, so that they can also learn and understand where the values come from and how different they are. In the next class, as I said, we will be taking a look at rate kinetic changes using Excel, and probably even going towards another software platform called MATLAB. Thank you.